In this video lecture, we will work through some example problems illustrating what happens when we're looking at sampling distributions and the normal distribution. Let's begin by recalling normal distribution computations. We noted that the normal distribution is the bell-shaped curve that describes most measurements. And we've also noted that because of the central limit theorem, the normal distribution, the bell curve, also describes how sample averages are distributed. Remember that with a normal distribution, about how much the data is within one standard deviation of the middle? One standard deviation was about 2/3 of the data. Next benchmark. 2 standard deviations gives us 95% of the data, and virtually all the data will be within 3 standard deviations. And so, for example, just to dust off some cobwebs, SAT math scores we know are normally distributed. The test is calibrated that way to have a mean of 500 and a standard deviation of 100. If we pick a person at random, what's the probability that individual has an SAT math score of 650 or higher? I'm going to ask you to take a minute, work through this problem. Dr. Asp, that is so unfair. That was from a previous module. You can't honestly expect us to remember back that far. Well, take a stab at things at least. Take a minute here, pause the video, see if you can work out the solution to this problem. I trust you began your solution by drawing a picture. Always, always, always draw a picture. We're looking for SAT scores of 650 or higher. The mean is 500. We're looking for this area under the curve. One way you could approach things is to find the z-score. A 650, 500's the mean. A 650 is 1.5 standard deviations above average. And we can use the norm.s.dist function in Excel for 1.5, and it'll spit out an area. Alternately, we could have said simply the norm.dist function. What's the probability associated with the 650 if the mean is 500 and the standard deviation is 100? Either way, we'll get an answer of 9332, but that's not our final answer. Remember, the Excel formula tells us the area from a certain point on down. 9332 is this area in blue. We want the area in red, which will be 1 minus that. About 6.68% of the population will have SAT maths of 650 or higher. So, second question, but related to this one. Same storyline, SAT math scores, but now we're going to select 4 people at random. What's the chance that their average score is 650 or higher? Now, before we compute anything, let's think for a minute here. Again, here's the storyline, SAT math scores. A minute ago, we worked out the chance that 1 person scores a 650 or higher. Now we want to know the chance that 4 people average out at 650 or higher. Think for just a second here. Will the answer to this second question be bigger than, the same as, or smaller than the average to the first question? Is this second probability, chance of getting 650 or higher from 4 people on average, going to be bigger, the same as, or smaller than the chance for just one person? It's going to be smaller. Why? Think about things. Remember, law of large numbers says that as we get more data, the distribution smooshes up. Things become less variable. There's more chance of winding up close to the middle, less chance of winding up out in the tails. We can even quantify how fast this happens. The standard deviation of the sampling distribution, of the sample mean, is a quantity that statisticians will also sometimes call the standard error. It's related to the amount of overall variability by this formula. Amount of variation in sample means is the amount of variation in individual observations divided by the square root of our sample size. Notice what happens as we get more data. As n gets bigger and bigger, this overall quantity will get smaller. As we get more data, we will get more accurate. But there is a square root downstairs. A diminishing return sets in. Let's see how it plays out in this problem. We're still looking for the area of 650 or higher. It works exactly the same as before, only different. We're comparing mean of 650, observation of 650 versus a mean of 500. But now our standard deviation is the standard deviation of this quantity, and this quantity now represents an average of 4 people. And so we need the standard deviation for 4 people, sigma individual standard deviation, divided by the square root of the sample size. In other words, finding a group of 4 people who average out this high, that's 3 standard deviations away from expected. Ultimately, you could use the norm dist function, mean of 650, observation of 650, mean of 500, but now our standard deviation is 100 over the square root of 4 because we're analyzing a sample mean. Either way, we get this as the lower area, and so 1 minus that is this tail. Finding one person up here, 650 or higher, that was pretty rare. But finding a committee of 4 that's going to be that talented, that will be exceedingly rare indeed. Let's work another example. We noted from a previous module, height of adult American women is normal, mean of 5'5", standard deviation of 3.5 inches. We're going to select 10 women at random. What's the chance their average height is 5'4" or taller? I will ask you to take a minute, work through this problem. Again, pause the video, work through a solution, then unpause the video, and we'll walk through the solution to the problem. I do encourage you, though, to pause the video and work through things. You learn by what you do far more than what you watch me doing. So pause the video here. course, you drew a picture. 5'5" is 65 inches. That's the mean. We want 5'4", 64 inches or taller. We can either work from the z-score, 64 inches versus the mean of 65. But this 64 represents not one person, it represents the average of 10 people. And so we use the standard deviation for an average, sigma, the individual standard deviation, divided by the square root of the sample size. Or we go straight to the norm.dist function. Observation of 64, mean of 65, standard error of 3.5 over square root of 10. Once again, that's this lower tail area. Because we drew a picture, we know we want the upper area, so we subtract off the blue shaded area. About 80% of the time, we'll have a group this tall or taller.